Welcome. So let's graph this one. All right, so factor the numerator and denominator and cancel any like factors that appear in both. So we are always going to factor first and check for any repeating factors. All right, so we have, all right, in the numerator there, I'll put it over here. All right, so we could factor out a 2. So if we factor out a 2, we have 2x squared minus x minus 1. All right, so now let's factor the rest. All right, so a is 2, b is -1, c is -1. We need two numbers that multiply to give us 2 times -1, so that's -2, but add to give us the b term of -1. Right, well, that's going to be -2 and 1, right? So -2 times 1 is -2. -2 plus 1 is -1. So just ignore the 2 for now. And we have 2x squared. We're going to replace the negative x with a -2x and a positive x. Just going back to what it was before somebody multiplied, right? And added terms together. So we have 2x squared minus 2x plus x minus 1. So we're just replacing the negative x with a -2x and an x. Notice I have not changed the value at all because -2x plus x equals -x. The first two are a group, the second two are a group. Factor out a greatest common factor, so the greatest common factor would be 2x. 2x squared divided by 2x is an x. 2x divided by 2x is 1, so we'll have x minus 1. And the only factor for x and 1 is 1. Right? And when we divide by 1, we still have x minus 1, which is our repeating factor. So we can factor out the repeating x minus 1, and we're left with 2x plus 1. All right, so that'll be the factors in the numerator. So we have f of x equals 2, and then we don't forget our 2 times x minus 1 times 2x plus 1. Now the denominator is just a difference of squares, so that's an easy factor. So square root minus square root plus square root. So this would be x minus 1 times x plus 1. And if you notice, we have the same factor in the numerator and denominator. We have an x minus 1. So we can cancel that out. So in reduced form, I guess I wrote too big over here. In a reduced form, I'll put it over here. All right, our function is f of x equals 2 times 2x plus 1 divided by x plus 1. And we could write it like that, or we could distribute the 2. It doesn't make a difference. Or we could write f of x equals 4x plus 2 over x plus 1. All right? All right, so now we're going to find the x-intercepts. And of course, we're not going to work with something we're not going to include something we canceled out. That's not going to be a point anymore. That's going to be a whole, right? We're only going to work with now the reduced function, right? So everything you find in the reduced function. The only thing you use the original function for is to find the value of the whole. All right. So now let's find the x-intercepts. Right? We find so a fraction is equal to 0 when the numerator is equal to 0. So we're going to set 4x plus 2 equal to 0. So subtract 2 from both sides. 4x is -2, and divide by 4. X is -2/4 or -1/2. So we have an x-intercept at the point -1/2, 0. We want to set the factors in the denominator equal to 0 and solve, and they'll either be a vertical asymptote or a whole. The one that remains, the x plus 1, is the vertical asymptote. So our vertical asymptote is where x plus 1 equals 0. Right? So x equals -1 is a vertical asymptote. The whole is the canceled factor. By the way, I don't know which ones are in your notes because I don't have them in front of me, so just pay close attention. All right, so the whole's the canceled factor. We canceled an x minus 1. So where x minus 1 equals 0, or x equals 1, is where the whole is. Now we need a y value for that whole. To find the y value, we're just going to substitute 1 back into the reduced function. Don't ever plug anything into the into the original function, right? Because things that you thought were an intercept won't be an intercept. Things that you thought were a vertical asymptote won't be a vertical asymptote, right? That's going to be a whole, right? So to have an accurate graph, we need to do everything with the reduced function. If you plug 1 into the original, you'll just have 0 over 0. And that doesn't have any meaning. All right, so f of 1 equals 4 times 1 plus 2 over 1 plus 1. So that's going to be 6, right? 4 plus 2, 6 divided by 2, or 3. So that means there's a whole at the point of the point 1, 3. It has to be a whole because 1 is a problem in the original function, right? That's why it's a whole and not anything else. All right, so now we need to find whether we have a horizontal asymptote or a slant asymptote. So we looked at the degree of the numerator and the denominator to determine. All right, so, and we're going to look at the reduced function. Boy, can I squeeze this in anywhere? I don't know, I'll try and squeeze it at the bottom. All right, so notice that the degree of the numerator n here is we just have an x, so that's degree 1. The degree of the denominator is also degree 1. So they are equal to one another. So that means the horizontal asymptote is just going to be the ratio of the coefficients. All right, so our horizontal asymptote is going to be, so in the numerator we have a 4, in the denominator we have a 1. So that's just y equals 4. That's our horizontal asymptote. Okay. So now we have found all the features we need. All we need now are some points. And we don't need too many because we have just one vertical asymptote. So let's go to the next page and graph. All right, so there I have the reduced function. The vertical asymptote was x equals -1. Let's graph that. The hole in the graph, right, was at 1, 3. And notice there's a hole already graphed. It could be on yours too if this is in your notes. Right, so I wanted to make sure you don't miss it. There's a giant hole right there in the graph. If you go near it, you'll be sucked in, and no one will ever see or hear from you again. And then the horizontal asymptote is just the ratio of the coefficients. Right, so that's going to be y equals 4 because we have we have an x in the numerator and x in the denominator. Coefficient on that leading term is 4 in the numerator, 1 in the denominator. So y equals 4 is the horizontal asymptote. All right, so let's plug in some points. You can count the whole as a point. All right, I mean the graph will go up to it and then jump over it and then continue on. So we can consider the whole. So 1, 3, and let's just note that's a whole. We had the y-intercept was 0, 2. And so those are both on the same side of the graph. They're on the right side of that vertical asymptote. And then we had the x-intercept was -1/2, 0. And that's also. So maybe I'll put them in order, I guess, numerically. So the largest there was the whole, which was 1, 3. And then we had 0, 2. And -1/2, 0. So they're all on the same side. So we need some on the other side. And we could get one on the other side of the hole just to make sure we know where to go after the hole. All right, so maybe we'll plug in 2. If we were to plug in 2, we would have 4 times 2 plus 2 divided by 2 plus 1. All right, so that's going to give us 10/3. So there, we may as well have one other point beyond that whole. And actually, next to the 1, 3 of them, we write in whole, because we want to make sure that you do not go through that hole. All right, and so now we need some values less than -1. I think -3 and -2 will be enough. All right, so we have 4 times -3 plus 2 divided by -3 plus 1. That gives us -12 plus 2, that's -10. Divided by -3 plus 1, that's -2, so that's just 5. And then if we plug in -2, 4 times -2 plus 2 divided by -2 plus 1, that's going to be -8 plus 2, that's -6, and that's just going to be -1, so that's 6. I think that should be okay. If we seem too far away from the asymptote, we can always plug in more. But let's graph the points we have now. All right, and I'll graph in blue, I guess. -3, 5, and -2, 6. That's probably sufficient. All right, so we will not cross the horizontal, and we will not cross the vertical. All right, there's that section of the graph. And then we have -1/2, 0. We have 0, 2. Right? And then we have the point 10/3, so 3 1/3. Right? So that gives us a good idea of the graph on this side. So of course we cannot cross the vertical asymptote. We go through those points, and then notice I'm coming right up to that hole, and then I'm going to stop, and I'm going to jump over the hole. That's me jumping over the hole. Do not go through the hole. No one may see you or hear from you again. Do not go through the hole. All right? And there we go. So now we just need domain and range. So this is very much like the graphs we started with, except we have a hole in it. All right? So these are really not very difficult to graph because thankfully the hole makes the degree smaller. All right, so let's do the domain and range. So we're going to take, of course, the vertical asymptote out. And if we think about it, so here are the values we need to take out, right? So x cannot equal the vertical asymptote. That's -1. X can also not equal the whole. Remember that in the original, up on top there, 1 was a problem, right? So 1 squared minus 1, that's 0. So x cannot equal either of those two things, right? So we have -∞ to -1. Then we skip over -1 to 1, and then 1 to infinity. Everything that makes that denominator equal to 0 before we reduced. Now the range, we're going to notice we're not crossing the horizontal asymptote. So here on our range, I'll put it over here. So y is not going to be equal to 4. But y can also not be equal to another value. Right? If x can't be 1, then y can't be 3. Because the only way I can get 3 is if I plug in 1. All right, so we're going to take both those values out. So you might find it easier, especially now when we've got a hole to deal with, to write those both down, and then you can see, okay, 3 is the smaller one. So we're going to go from -∞ to 3, and then from 3 to 4, and from 4 to infinity. Because everything except for the horizontal asymptote, which we don't cross, and the whole is fine for the y values. Right? And let's do one last thing. Let's do end behavior. So the whole is not going to have any impact, by the way, on end behavior. So our function is going to approach the horizontal asymptote. So our function approaches 4 as x approaches -∞. As we get close to that vertical asymptote, as we come from the left, f of x approaches infinity. As x approaches -1 from the left, as we come from the right, f of x approaches negative infinity. Approaches negative 1 from the right. And then as x gets larger, y heads right back to that asymptote. So f of x approaches 4 as x approaches infinity. And there we go. I'm just going to take out the arrows because we don't need those in there to stay. All right? And so in the next podcast, we'll see another graph that has a hole. All right? So thanks for watching, and bye for now.